So in 12.1, what we're going to be looking at this time is, again, we're doing hypothesis testing. But if you remember in chapter 11, we were hypothesis testing either about a mean or a population proportion, where we were saying, well, we think the mean is this thing, but let's test whether it's actually different than, greater than, or less than what we thought it was. And that was based off of some sample data that we got. This time what we're doing is we are comparing two means to one another. So we're saying, okay, I have these two different populations and I want to compare their means. So I'm going to take a sample from each one of my populations. I'm going to look at some data for these samples and I'm going to compare that sample data. And based on what that tells me, it's going to tell me whether those population means are the same, different, greater than, or less than one another. Okay. So all we are doing now is just comparing two different population means. This is done in very much the same way. We're dealing with test statistics. We're going to link this to confidence intervals, and we're going to see how to do this on a calculator. The first thing that we are going to look at is when you know what the population standard deviations are for each one of the populations. So let's say you have this population here and another population here. Okay, we'll say that this is population 1 and this is population 2. Okay, population 1 is going to have mean mu1, population 2 is going to have mean mu2. And then out of each of those, we're going to take some sample. Okay, so this is going to be sample 1. And then we're going to take a sample out of this other population and we're going to call this sample 2. Okay, sample 1 is going to have mean x1 bar and sample 2 is going to have mean x2 bar. Okay, now first we're going to assume that we know our population standard deviations. Okay, so we're going to assume that we know what the standard deviations are for each one of our populations. So let's say that population 1 has standard deviation sigma 1 and population 2 has standard deviation sigma 2. Okay, now if you remember back to chapter 11, if we knew what the population standard deviations were, we used a z-test. If we didn't know the population standard deviations, it meant we had to use our sample standard deviations, which meant we had to use a t-test. But in this case, because we know our population standard deviations, we know that it is going to be some kind of z-test. Okay, so keep that in mind as we go through this. Why is all of this useful? The reason that we like to do this is comparing two populations to one another. It's done a lot in things like, let's say that you were a car rental company and you wanted to compare what the gas mileage was for two different models of car. Okay, you would like the gas mileage on a car to be pretty good, okay, because it's cheaper. Okay, so maybe you could be a car company and you just wanted to know which make or model had better gas mileage. So you're going to take each one of those models of car and you're going to look at the gas mileage for the whole population. Okay, and you want to compare them. Okay, so you want to compare the gas mileage on each one of these cars. That's where it's useful. Okay, any kind of comparison thing is where this becomes useful. Okay, so what we are looking at here is, remember before when we were dealing with looking at whether the population mean equaled this particular value or whether it was different than, less than, or greater than a particular value. In this case, what we want to know is, are our sample means close enough together that we can assume that our population means are equal? So what we want to look at is, are the sample means close enough together if they're close enough to one another, then we can probably assume that the populations from which they come from have the same mean. Okay, if you take samples out of two different populations, as long as you've taken a representative sample, if those sample means are close enough, it's probably a pretty good guess that the populations that which they come from have the same mean. Okay, so if the sample means are close enough to one another, it probably means that your population means are very close together, which means that you could assume that they're almost equal. Okay, so are the sample means close enough to one another that we can assume that the population means are equal? Okay, so if we want to see if our sample means are close enough together, okay, I want to look at the difference between my sample means. So this time, rather than looking at the distribution of a single sample mean where the sample comes from a single population, what I now want to do is look at the difference between two sample means and look at the distribution of the difference between the sample means. So if you remember before, when we had one population, we took one sample from that one population and then we took the distribution of the sample means, and that is what gave us that test statistic that we were using in our hypothesis tests. What we are doing now is that we need to look at the distribution of the difference between the sample means, because we want to see how they differ from one another. Are they close enough together or too far apart? So now, because of this, we need to look at the distribution of x1 bar minus x2 bar. So I'm looking at the distribution of the difference between the sample means. This is going to change your test statistic. Okay, it's going to be slightly different than it was before, obviously, because now you've got x1 bar and x2 bar. Okay, it's not immediately obvious what this is going to be. It's just going to have to be one of these things that you kind of remember the formula for or write it down and have it next to you. You shouldn't need to calculate this too much because your calculator will do this for you when I show you how to do the short way, but just be aware of it, okay? But most of the time you can use a calculator. So this time, okay, we'll talk through this. Your test statistic, if you were conducting a hypothesis test here, your test statistic is going to be Z is equal to, it's a pretty long formula, but we'll talk about it after we've written it down. Okay. So the setup of this test statistic should remind you very much of what we've had before, okay? Whenever we were looking at a test statistic before, we always had, let's say, like the sample mean was here, and then the population mean was here, and then the standard deviation was always here. So it was always the sample mean minus the population mean divided by that standard deviation of the sample means, which always involves something to do with the sample size. This is very much the same, okay? We've got the difference in the sample means minus the difference in the population means, and then this term on the denominator is actually the standard deviation of the difference in the sample means. So it does look different this time because we've got two different sample means, two different population means, but it is very much the same setup. Okay, so keep this test statistic in mind as you go through this. Okay, as I said, your calculator will do it for you when you conduct one of these tests, but make sure that you know where it comes from, and it's a very similar setup to what we've had before. So when do we use this test statistic? We use this test statistic when we do these hypothesis tests. And when we conduct a hypothesis test, what we're actually testing is whether the population means are the same or whether they are different, less than, or greater than one another. Okay, so basically we want to see if they're equal or not. So first thing we have to do is to write down our null and alternative hypotheses. Well, our null hypothesis is always equality, okay? So we're going to assume that our two means are equal to one another. So whenever you do a hypothesis test, when you're doing this about two means, okay, your null hypothesis is always that mu1 would equal mu2, that the two population means are equal. Another way to write mu1 is equal to mu2 is to write mu1 minus mu2 is 0. Okay, that assumes that those two are equal. Your alternative hypothesis can have three different forms, okay, as always. You can have that mu1 minus mu2 doesn't equal 0. That's a two-sided hypothesis. You can have that they're greater than 0 or less than 0. Okay? Now, bear in mind what each one of these means. Okay? If mu1 minus mu2 doesn't equal 0, it just means that mu1 doesn't equal mu2. It just shows that they are different. So whenever you get a problem and it says, conduct this hypothesis to see whether the means are different, that's when you use do not equal. Okay? For greater than, if I put a greater than 0 in there, if you rearrange that formula, that would be that mu1 is greater than mu2. Okay, so that shows that the first population mean is greater than the second one. When mu1 minus mu2 is less than 0, that's the same thing as saying mu1 is less than mu2. So the first population mean is less than the second population mean. So it depends what the question is asking. But keep that in mind and make sure that you have these means the correct way around depending on what the problem is asking. Okay? So that is your null and alternative hypothesis. Okay? Now, you're going to run, in this case, as I said, you know what your population standard deviations are. Because you know what your population standard deviations are, you're going to be using some kind of a z-test, okay, as always. But in this one, we're going to be conducting a two-sample z-test. It's not a standard z-test that we've done before where we've had one population and we've taken a sample from that one population. In this case, you've got two populations, each one of which has a sample. So we've got two samples. So you're going to run on your calculator a two-sample z-test. Okay. We're going to look at a situation in a minute where we don't know those population standard deviations. So if you don't know sigma 1 and sigma 2, it's going to be a two-sample t-test, but that one's slightly more complicated, so we'll look at that separately in a minute. But in this case, because we know our population standard deviations, we're going to run a two-sample z-test on the calculator. What that will do is it's going to give you the test statistic, okay, as always. So if a problem ever asks you for the test statistic, you can go ahead, conduct the whole test on the calculator, and it will give you that test statistic that you could, if you wanted to, compare to a critical value. Critical value is still found in the same way as before, where they're going to give you that significance level alpha. You can draw out your normal curve. You can say, okay, let's say your significance level is 0.05. That means that you want to reject your null hypothesis 5% of the time and fail to reject it 95% of the time, depending on whether it's a left-tailed, right-tailed, or two-tailed hypothesis. Depends on how you draw that normal curve and where your tails are. And that all depends on which one of these three alternative hypotheses you have. Okay, so when it comes to a critical value, it is very much the same as what we've had before. Okay. Now, the other thing to be aware of, as I've just said, is that significance level alpha. Okay, a problem is going to give you a significance level alpha. So what you can do when you conduct this two-sample z-test is you can see what that p-value is. Okay, the p-value that we've talked about before. That is the probability of having a test statistic that is at least as extreme as what you have up here. So whatever z value you get here for this test statistic, okay, the p-value is the probability of having a test statistic that is at least as extreme as this one, okay? Now, you're going to conduct this thing, you're going to find what the p-value is, and you're going to compare it to that significance level alpha, okay? If p is less than alpha, so if you get p less than alpha, you're going to reject the null hypothesis, as always, because that means that your test statistic falls in that danger zone, okay? It falls past where that critical value is, which means it falls in the danger zone where we have to reject the null hypothesis, okay? If p is greater than alpha, okay, that's going to mean that your sample means are close enough together that we can assume that our population means are equal. And therefore we can fail to reject our null hypothesis. We can accept it for what it is and say that mu1 is equal to mu2. So if p is greater than alpha, you're going to fail to reject, as always. Okay, so it all depends. It's pretty much exactly the same as last time. You're just running a slightly different test because you're now comparing two different means. Okay, I'm going to go through a very quick example here. For those of you that want to look on the Google Drive at the notes, it is at the bottom of page 3 of my notes for this chapter. And it's an example of a 2-sample test, and we're going to run this on the calculator as well. Okay, so it says that a medical researcher wants to compare the pulse rates of smokers and non-smokers. He believes that the pulse rate for smokers and non-smokers is different and wants to test this claim at the 0.1 level of significance. So we already know from the top line what our null and alternative hypotheses are going to be, because it says that he believes that the pulse rate for smokers and non-smokers is different. Okay, so we know that our alternative hypothesis is going to be two-sided. We've got a two-tailed test here. So before we even start, we know our null hypothesis is always going to be mu1 minus mu2 is equal to 0. Our alternative hypothesis is going to be that they do not equal 0, because we're just going to be looking at the fact that mu1 doesn't equal mu2. That's what we're testing. Okay, and our level of significance, again from the top, is 0.1. Then it says a sample of 60 smokers, okay, has a mean pulse rate of 84. So we've got 60 smokers have a mean pulse rate of 84. So that tells us that the first sample size is 60 and their mean pulse rate, so the first sample mean, is 84. And a sample of 49 non-smokers, so our second sample, has 49 people in it, and their mean pulse rate is, it's 82. Okay, so I've got 49 non-smokers have a mean pulse rate of 82 and 60 smokers have a mean pulse rate of 84. Okay, the population standard deviation of the pulse rates is known to be 10 for smokers, so that tells me that sigma 1 is 10, and 6 for non-smokers. Okay, make sure you get these the right way around, so make sure that you match them up to the correct populations and the correct samples. Okay, then you're going to let mu1 be the true mean pulse rate for smokers and mu2 be the true mean pulse rate for non-smokers. So this agrees with what we've just done, because if mu1 is the true mean pulse rate for smokers, okay, that's for the whole population, that means that population 1 has mean mu1, and from that we take sample 1. Okay, so that was our first sample, and our first population are all to do with the smokers. Our second sample, which comes from our second population, comes from the non-smokers. So we've got everything the right way around. Just make sure that you do get this the right way around, so you get your means the right way around. Because especially when you have like something like a less than or a greater than here, you may get it the wrong way around if you don't agree with what their means are. So if, like, let's say mu1 was non-smokers, okay, everything here would be switched. Okay, so please keep that in mind when you do this. So we've got all of this information. What I now want to do is to run this test. So if you go to stat tests. And then the third option is a 2-sample z-test. Okay, we know our population standard deviations. It's a z-test. We've got 2 samples, each one from a different population. So we've got 2 populations and 2 samples. So it's going to be a 2-sample z-test. Make sure you can pick out what test you need to conduct. Okay, depending on what is given in the problem. Where the input is stats. Okay, we're inputting statistics here. Sigma 1 is going to be 10. Sigma 2 is going to be 6. X1 bar is our sample mean for our first sample, which is 84. N1 is our sample size of the first sample, which is 60. Then X2 bar is the sample mean for our second sample, which was 82. N2 is our sample size from the second sample, which is 49. Then what we need to do is to determine whether we've got a does not equal, a less than, or a greater than. In this case, our alternative is a does not equal, and we can go ahead and calculate. Now, reading through this, it looks very similar to what we've had before. The top line corresponds to what your alternative hypothesis is. It's just rearranged. So, as I said, mu1 minus mu2 doesn't equal 0. It's the same thing as saying mu1 doesn't equal mu2. Okay, just rearrange that formula. Z is going to be what your test statistic is. So if I did want to take a test statistic and compare it to a critical value, okay, you could go ahead and do that. In this case, Z is 1.2906. Okay, so that is our test statistic. P, okay, is the probability of having a test statistic that is at least as extreme as the one I have just found. So it's the probability of having a test statistic that's at least that extreme. Okay. Now, as always, you compare the p-value to alpha. In this case, p is 0.1968. P is greater than our significance level alpha. So p is greater than alpha. So we're going to fail to reject our null hypothesis. Relate it back to the problem. We're failing to reject our null hypothesis. That means we're accepting it for what it is, and we're saying that mu1 minus mu2 is equal to 0. That means that our sample means were close enough together, 82 and 84 were close enough together that we can still say that our population means are equal. Okay, so because we're failing to reject our null hypothesis, that means we assume that mu1 is equal to mu2, so our population means are the same. Relate it back to the problem. That means that we think that the mean pulse rates of smokers and non-smokers is the same. Okay, so always relate it back to the problem. Now, another way that we could have conducted this problem, and this problem in particular, is by using confidence intervals. Okay, you only were able to use confidence intervals if you look back in 11.3. We could only use confidence intervals in hypothesis testing when we had a two-sided hypothesis. So when we've got that two-sided alternative hypothesis that does not equals, okay, that means that we can go ahead and use a confidence interval instead of using one of these two-sample z-tests, okay? This time it is slightly different. If you remember, when we conducted a confidence interval in 11.3 in order to do one of these hypothesis tests, what you did was you went ahead, found the confidence interval, and then you saw if the population mean value that you thought that value was, you saw if it was inside that interval. If it was, then you failed to reject the null hypothesis. If it wasn't, then you rejected the null hypothesis, okay? So go back and look at 11.3 when we did that. So when we did that, okay, again back in 11.3, you had something, your null and alternative hypothesis looks something like this, okay? So you had a two-sided alternative hypothesis. Your null hypothesis said, we think that the mean is equal to this mu0 value, okay? 3, 4, 5, 6, it doesn't matter what the value was, okay? And then the alternative hypothesis was we were hypothesizing that the mean did not equal that value. You went ahead, given the sample data, you conducted the confidence interval, and then you saw whether this value was actually inside that confidence interval. If that value was inside the confidence interval, we failed to reject our null hypothesis. Okay, we said, well, that means that our mean is close enough to our sample mean, therefore we're going to fail to reject the null hypothesis. But if that value fell outside of that range, it meant that our population mean was far enough away from our sample mean that we could no longer accept that null hypothesis. We had to reject that null hypothesis in favour of the alternative and say that the mean was not equal to that value. Okay, so we always looked at whether this value was inside the confidence interval or not. If we now relate this to the problem that we have, okay, our null hypothesis is that mu1 minus mu2 is equal to 0. Okay, that means that mu1 is equal to mu2. Our alternative hypothesis, again, we can only do two-sided alternative hypotheses if we want to do a confidence interval. Okay, you cannot do a confidence interval if you have a one-sided, if you have a greater than or less than. Our alternative hypothesis was that it does not equal 0. So this time what I'm going to do is, given the sample data, I'm going to conduct this confidence interval, okay, and I'll go through what the confidence interval is in a minute. You're going to find a confidence interval, and this time what you're looking for is whether 0 falls in that confidence interval. If 0 does fall in that confidence interval, it means that mu1 and mu2 are close enough together that we can consider them equal. If 0 does not fall in that interval, then we have to say that it's different to 0. We have to say that mu1 does not equal mu2. Okay, so this time what we're going to be doing is conducting this confidence interval and then seeing whether 0 lies in it. Okay, so our confidence interval this time, again, if you have a two-sided alternative hypothesis, our confidence interval is going to be x1 bar minus x2 bar plus or minus z of alpha over 2 multiplied by the standard deviation of the difference in the sample means, which we said was this thing here. It was the denominator of that fraction when we did the test statistic. Okay, this z value here, okay, that was the critical value. Okay, so whenever we did like test statistics and critical values and that stuff, that is the critical value. Okay, so you can go ahead and figure out x1 bar minus x2 bar minus this value. That will give you your lower bound for the confidence interval, and x1 bar minus x2 bar plus that term is going to give you the upper bound of our confidence interval. Okay, that's a lot of work to do. We don't want to be doing all of that, okay? For a start, this term is horrible, but also we have to then compute what the critical value is. So there is a much easier way of doing this again on your calculator. So if you go to Stat and go across to Tests, again, we know what sigma 1 and sigma 2 are. We have our population standard deviations. So we can go ahead and use a two-sample z interval, okay? It's a z interval, not a t interval. Okay, so a two-sample z interval. Okay, in my calculator, let me check what number it is. It's option 9 on that list. You're inputting statistics again, okay, and you're going to go down and input all of the values and all the data. Okay, so it's, if we went back, we can do this for the example that we have. Okay, let me, oh, it was this slide here. Okay. If we went ahead and did that same example, but this time, because we've got a two-sided alternative hypothesis here, so let's conduct a confidence interval, see what our confidence interval is, and then we can see whether 0 lies in that confidence interval, and we can see if we get the exact same decision at the end, okay? So inputting the statistics, sigma 1 again was 10, sigma 2 is 6, x1 bar is 84, n1 is 60, x2 bar is 82 and n2 is 49. Okay, confidence level. It's always 1 minus alpha. Okay, alpha in this case was 0.1, so our confidence level is 0.9. We want to be 90% confident in this case that mu1 minus mu2, being 0, falls in this confidence interval. Okay, so we go ahead and we calculate. So the confidence interval that I get in this case is negative 0.5489 and 4.5489. Okay, so what I want to see is if 0 falls in this confidence interval. Okay, looking back at our formula, if 0 falls in that interval, that means that these two things, x1 bar and x2 bar, are close enough together that I can consider the population means to be equal. Okay, if 0 falls in this interval, it means these two things are close enough together, okay, because this thing's going to be really, really small, okay, in that case. If 0 falls in the interval, these two things are close enough together that I can consider this thing to be true. Mu1 minus mu2 is equal to 0, because if they're close enough together, I can consider these population means to be equal, if my sample means are close enough together, okay? So 0 does fall in this interval. That means that I can fail to reject my null hypothesis. So if 0 falls in the interval, it means the sample means are close enough together that we can consider the population means to be equal. Okay, so that means we fail to reject the null hypothesis. Okay, so in our case here, 0 falls in that interval. That means we fail to reject the null hypothesis, which means that we can consider the mean pulse rates of smokers and non-smokers to be equal. Exactly what we have said here. Okay, so when you have a two-sided alternative hypothesis, you can go ahead and either conduct this test and you can compare P and alpha as normal, or you can go ahead and do one of these confidence intervals. Okay, if 0 falls in that confidence interval, it means your sample means are close enough together that you can consider the population means to be equal, and therefore you're going to fail to reject the null hypothesis if 0 falls in this interval. If 0 falls outside the interval, it means your sample means are far enough apart that you can no longer consider your population means to be equal, and therefore you're going to reject the null hypothesis if 0 falls outside of that range.